This video introduces a TTR-based reward shaping method for reinforcement learning with implicit model priors. Sequential decision-making is a fundamental problem in robotics. Reinforcement learning and optimal control are two main methods to solve such problem. In particular, model-free RL is the most scalable and flexible and directly learns to map high-dimensional states to actions, but suffers from poor data efficiency. Model-based RL learns based on an estimated model, thus requires less data, but is easily affected by model bias. Optimal control does not require any data to generate optimal solution, but requires a known model and a full state information, and cannot scale to high-dimensional models. Our method combines optimal control and model-free RL to achieve flexibility, scalability, and good data efficiency. A TTR function maps a robot internal state to the minimal arrival time to the goal, assuming a model of the robot dynamics. In general, we start with a robotics problem in the real world in the form of unknown MDP. Our running example involves a car with laser sensors and a full status with 13 dimensions, including position, heading, speed, angular speed, and 8 laser range readings. Since the model is unknown and high-dimensional, the TTR function for this system cannot be computed. Therefore, we pick up a subset of the full state and model a simplified system using an ordinary differential equation. Here we choose the position and heading as the state of the approximate model because it sufficiently captures the k-dynamics of the robotics behavior. Once a low-dimensional approximate model is obtained, we can derive the TTR function by solving our associated Hamilton-Jacobi PDE. Then we simply use negative TTR function as a reward function for the higher dimensional RL problem because the state with lower arrival time to the goal should be given a higher reward. As a result, the TTR-based reward can be easily integrated into RL process without altering any model-free algorithm structure. We evaluate our method on a quadruple goal-oriented task. As shown here, TTR-based reward achieves higher success rate with relatively fewer learning iterations under 3 different model-free algorithms. In contrast, sparse and distance-based reward only perform relatively good under TRPO, but very poor and unstable under DTPG and PBO algorithms. Therefore, TTR-based reward achieves the best result regarding learning efficiency and success rate. From this real-time performance visualization in Gazebo simulator, our method works well on the simple ground robot as well as the highly dynamic quadruple system. We also use frequency heat maps of target positional states during learning to illustrate the effectiveness of our approach. Here we can observe that TTR-based reward leads to a near-complete trajectories during first 40 learning iterations, which suggests TTR functions guiding learning effectively. In contrast, distance-based reward results in a more spread-out distribution of positions, and a sparse reward shows even more unnecessary exploration. In summary, our approach accelerates model-free RL with implicit system dynamics priors and can act like a wrapper for any model-free algorithm or technique. It also provides a distinct reward shaping option which requires little human engineering.